Chapter 6, Lecture 3, using Routh-Hurwitz for design. So in this lecture, we're going to take a look at using the Routh-Hurwitz to design systems. So here, given a transfer function where the gain k appears in the denominator, we want to use the Routh-Hurwitz method to find the range of k, the values that ensure stability. So let's take a look at a particular example. So we have a closed loop transfer function and we have a characteristic equation, which that's the denominator. Given by the following function, we want to find the values of k that make the system stable. So the first thing we do is we write the root table. So here's our characteristic equation. We fill out the first column, second column, etc., and then we construct their values using our method we did in the previous lecture. So now we apply the stability conditions. So the elements in our first column, 1, that's certainly greater than 0, so that checks out. 2 plus k, greater than 0, that means k is greater than minus 2. And this condition here, when is this value greater than 0? Well, we can simplify the numerator by multiplying this out. So this third row here becomes the following value. This is simplified to this here, which I've shown here. So here, we need to know when this expression is greater than 0, and we have to consider the denominator as well. So to ensure stability, we want 2 plus k to be greater than 0, which means k is greater than minus 2, or we want the numerator to be greater than 0. So here we can this is a quadratic, so we can use the quadratic equation on that. So we plug this in the quadratic equation, we get two roots. We get minus 2.59 and 0.26. So here, it's positive when k is less than minus 2.59 or k is greater than 0.26. So here we have to, we have the earlier condition is 2, that k had to be greater than minus 2. So we have to take all these into account. So when you do that, what you end up with is that here, again, our final condition is that k has to be greater than 0.26. Because if you satisfy this condition, you satisfy that condition. This is the more limiting condition, is k is greater than 0.26. So here, the system is stable for all k greater than 0.26. So here, without solving for poles, the Routh-Hurwitz gives us a closed form design constraint for a stable system. So this is why it's pretty powerful for design. It allows us to determine the exact parameter bounds and avoids guessing or numerical trial and error. This is useful to tune controller gains and feedback system parameters. And you can even use this to sort of determine pole locations indirectly.